Hello guys, welcome to another episode of Sound Talk Show. Today's topic is Unicode. What is Unicode? What is ASCII? What is character set? What is encoding? What is UTF-8 and what is UTF-16? And all these topics, and what is emoji? But this is for programmers. So if you program in Python, in C, in Java, whatever language, JavaScript, Golang, or Wolfram language, you actually need to know about encoding, about character set, about these issues, okay? And that's today's topic for programmers. So now, if you have comments and questions, post it there, okay? I love to see it. Okay, so I'm gonna tell you and what's a Codepoint, what is all these things, UTF-8, UTF-16, and what is a surrogate pair, and what is byte order, and what is BOM, byte order mark. For the first 15 years of programming, I started programming in 1992. Okay, starting with Wolfram language. I coded Wolfram language every day, several hours, for about 8 years, 1992 to 1998. That is every day. And then I started to code Perl and Unix stuff, Bash and Unix and Java. And then later on, the next decade, Python and all other PHP and all the other languages and Emac Lisp. But, for the first 15 or 20 years, I don't really understand encoding because I'm not a low-level programmer. Of those of you, if you are programming, if C language or Java is your first language, those low-level languages, or even Golang or C++. Now, if you are those language programmers, if that's your main thing, if that's your first language, then you likely understand more about encoding. Okay, sorry, my alarm clock, I need to shut it off. So if you are a C, low-level language, you likely understand bytes and encoding issues because especially in C, you deal with bytes. But these programmers, especially C programmers, they don't know about Unicode. When it comes to Unicode emoji, they don't understand. They tend to stick with ASCII. Whenever you have an emoji characters, they refrain from it. So encoding. So you actually need to know. It's actually so if you are a high-level programmer, like me, then you need to know it less, but eventually you need to know because every character, even if you don't program, every character, every file, when you open, encoding is involved because all the letters ABC, the computer cannot store ABC like characters. They actually transform them into binary numbers. So this process, for example, the character A, let's say, what is this character? So you can, in Emacs, you can say describe char, and you get this panel of information about this character. You can see, A Codepoint 65. What does that mean? And here's the octal number for 65, and here's a hexadecimal 41 for 65. What does it mean? What's the code point? So that's encoding because you need it. Even if you open a file in browser, if you got the encoding wrong, then you got gibberish. Sometimes you'll see, and even in Emacs, for example, line ending return, sometimes you'll see these characters all over every line, at the end of every line. So all these are related to encoding. So let me show you some. So I'm going to explain, I'm actually starting to explain already encoding, why you need it. So, but let me show you some of the, all the talk I do today is already written. So all you have to do is you go to search for ASCII Unicode. Then near the bottom, the panel, you can see Unicode for programmers. And here is a whole lot of articles. It's all written, so you don't have to take notes. You can just read them. ASCII Unicode. Okay, so explain about encoding and character set and Codepoint. Then you have different languages, how they deal with encoding, lots of issues. For example, this one is interesting. Is the problem of symbol congestion in computer languages. ASCII jam versus Unicode. Especially so if you are a C Java programmer, this hits you because this is a problem for you because, for example, here is a regular expression. You can let's go there. Okay, let's magnify. Well, open image. You see, here is a regular expression in Emacs Lisp, and it's not Emacs Lisp is the worst. You have the toothpick syndrome, the \escape. So for example, if you're a programmer, you know about escape characters, right? \. But in PowerShell, it's a different character. In PowerShell, the escape character is the accent. Let's magnify. Actually, that's the. This is so accent character. This is escape. So anyway, the point is you have to deal with escape. Okay, maybe not that. I have it written somewhere. So, but you see this regular expression. So in Python, in Java, in any language, you have this kind of thing. Hard to understand, but it would be much better if you allow Unicode characters. So I'm kind of digressing, but let me show you. So encoding, okay, so let me show you. Right now I'm talking about all the consequences and related, things to encoding. For example, Unicode. Why is it invented? If you don't have Unicode, what happens? What is the effect? Why don't we stop? All this emoji? Then what happens to your programming language? Lots of things. So that's what I'm talking about. Regular expression is an example because you only have limited number of characters. So you started to need escape and all sort of other things. So you have ASCII jam, and you have like the same symbol used for so many things. Especially, one of the major problem in many languages, and including computer languages, like not programming languages, like HTML, you have the so-called entities. Very complex. These are entities. In other words, it's an escape mechanism, more typically known to programmers. This is actually a escape mechanism to allows you to enter some character, but without the character itself. So you can type ampersand that, then a semicolon, then you get this character. So this is entity list. Now I would say this is a consequence when you don't have Unicode. So your source code becomes extremely complex, impossible to read. Suppose you are speaking French. Now in French, you need acute E. So for example, you need acute E. So let's see. Let's search for acute. So you have acute A. So let's search for E acute. There it is. So in many European languages, you need these characters frequently. Now imagine you are writing an essay or whatever. You are writing an article, and every occurrence of this E, you have to say ampersand E acute semicolon. That's fucked up. That is a consequence when you don't have Unicode. Now most programmers, you don't think of it. This doesn't occur to you, but it occurs when you have regular expression. Now most of you know which regular expression is hard to read, and why? Well, part of the reason is that they ASCII jam. Like when that's one of the consequence, ASCII jam. But programmers, you don't think of, usually this doesn't occur to you because you are so used to, the typical Stack Overflow, the Hacker News, typical. They don't think too much. And are there languages that fully embraces Unicode? Yes. For example, Fortress. Okay, let me show you an example. Of Fortress, lots of problems, and also this ampersand encoding in URL. That is extremely complex, okay? Ampersand encoding, very confusing. Even, different browsers, they don't agree on what exactly it should be. For example, when you have an ampersand in the URL, for example, when you go to Amazon, when there's a query, that happens a lot. But whether you should encode that, then you have the issue of different encoding, because sometimes it's like you see %26, that's URL encoding. Then you have the ampersand encoding. So you have two different encodings in the URL syntax. Extremely confusing, okay? This problem will not happen when you have the Unicode in the beginning. Let's say if we have Unicode in 1960s, all these problems doesn't occur. And let me tell you another significant, the most significant problem about the ASCII jump Unicode, consequences is that when you have escape, for example, in, let's say, JavaScript, or in C, in Java, in Perl, in Python, in Ruby, all the same, okay? So, but right now I'm using JavaScript, for example. So let's see, I want a constant, okay, x equals to some \n thing, So let's console log x print x, okay, evaluate it. You can see the output is something in 2 lines. Why? Because you have this escape mechanism /n. You probably don't think this is complex, but this is actually very complex. In different languages, they have elaborate different escape mechanisms. So what's the problem? The problem is that, so in Emacs, for example, I want to call a shell command. So you want to pass some arguments, but often when you do, let's say you want to pass a regular expression, you want to call grep in Emacs. You want Emacs in your application to call a grep command of a different application. So you need to pass the arguments. Let's say you need to pass a regular expression, so full of the \n slashes. But then you have the essentially escape problem, encoding problem, because it's almost impossible to translate correctly because you are going through different layers. So anyway, that's a very common problem, very, very common problem, almost unsolvable. And this encoding, this escape mechanism problem happens more severely when you have nested parsing. For example, if you are writing a regular expression, usually it's used to match some text, right? Now, but suppose you are writing a regular expression to try to search through all your Python code that contains regular expression. You want to use a regular expression to see if a particular regular expression happens in your code. That is when you have hell, and it basically, practically speaking, impossible to do. Why does that occur? That occur because of the ASCII jam issue. Okay, most programmers don't know about this. So that's an example of ASCII jam. When you use regular expression, trying to find regular expression, when you have some sort of nested thing going on. Another example of this is when you have HTML embedded in HTML. For example, let me show you. Okay, so let's go back. So let's say I want the HTML. So you are looking at Talk Show. This is a HTML file, right? And so I want to tell people how do you, I want to teach people how do you have a paragraph. So for example, I can write, this is how you do paragraph. Use this p tag, okay? So that's a paragraph, you see. But if you show, let's say, use p tag like this, okay? Let's see. Okay, so this is the HTML source code. Now let's show in browser. Let's see what happens. You see, this is how you do paragraph. Use p tag like this, empty. Why? Because the p tag is, paragraph tag. So what you need to do, you need to encode these angle brackets. So, I can do it. So this is what you actually want. Actually, you don't actually need that. So this is what you want, okay? So now go to the browser. Now watch this part. Show. So you see, so this is an example when you have, again, nested encoding that creates a lot of problem. This is a huge problem, just like regular expression, searching for regular expression. Because suppose I'm done with this, but tomorrow or next year, next programmer or whatever deal with, you need to process, you need to change something. This often may become encoded wrong because it may become encoded twice. So for example, I can encode this ampersand by, let's see what is the key to encode that ampersand. Yeah, okay, so you have but anyway, so I forgot what's the oops, what did I do? Yeah, so let me do this, okay? So hold on a second, cancel that. So here is all commands, search for encode. There it is, tab 1. XHTML encode ampersand entity, okay? So let me show you a different example. Let's say sum, okay? Paragraph, now you want to encode them, so you select them, tab 1. So you see, and if you want to, but sometimes it happens if you encoded this twice, tab 1, so it becomes that. And that becomes, let's show in browser, you can see what happens. You see, you get that. So this is the encoding escape, encoding problem. This is actually not encoding. This is an escape mechanism problem. Okay, so these are consequences when you have the ASCII jam. Okay, so actually let's talk about the actual today's topic. Okay, let's begin to talk about. So I already spent 20 minutes on introduction. So encoding. Okay, let's begin to talk about encoding. Now we got some spammers here. Shit. Okay, let's talk about some encoding problem, okay? I mean the actual tutorial about Unicode, okay? So you need encoding. So what is encoding? Encoding is a way to transform each character to a sequence of binary numbers, ones and zeros, okay? So let me show you why do you need to do it. Encoding is a way to transform a sequence of characters or text or whatever to ones and zero. Why do you need to do that? Because computers, the chips, the electronics, they have, electricity, and the way they work is that you have high voltage or low voltage. High voltage means 1, low voltage means 0, represented by 1 and 0. So basically, at the core, everything is just 1 and 0. So that's binary number, okay? So you can see an example of binary number, okay? So how does binary number work? Let me explain. So usually when we write numbers by what's called decimal notation system. Now, the way this is a number notation system, okay? There are many ways to write a number. For example, you have a Roman numeral, V stand for 5, I stand for 1, 2I stand for 2. That's another numerical, number notation system. In China, in India, in other countries, in Maya, or Asian civilizations, or in Egypt, they all have different ways to write numbers. But today, the standard, almost the universal is a Arabic numeral system. Anyways, but this system is a notational system for writing numbers. And the way this notation works is that you have 10 distinct symbols, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, so you have 10 distinct symbols. Now, this may be trivial. I'm explaining this because if you understand it, then you clearly understand binary numbers, octal numbers, hexadecimal numbers, and numbers of any base. Not just, typical programmers, they just understand, binary, hexadecimal. If you say 17-based number, they go, what? they don't understand the mathematical concept behind it. Okay, so a decimal notation system is 10 different symbols. Each one represent a number. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have the 0, represent nothing. But what if you want to say 10? You don't have you don't have a symbol for 10. So what you do is that when you reached 8, the next number is 9. When you reach 9, the next number is 10. But you don't have symbols for it anymore. So you put an extra symbol. You put your beginning symbol 1, because there's no symbol after 9. So you put 1, you start over 1, you put it down, then you put a 0 after that. This is how the decimal number notation system works. Now, so remember, you begin with 10 distinct symbols, 0 to 9. Okay, and when you are out of the numbers, you just put 2 digits, one after another, start over. Okay, so in the same way, this is how binary number works. You have only 2 distinct symbols, 0 and 1. So 0 is just 0, 1 is just 1. Now, if you want to represent 2, what to do? You don't have a number, you don't have a symbol for 2. Well, you start over. So you start with 1 again, put it down, then you follow it by a 0. So the next number you increase again, what comes after 0 is 1. So you just put 11, 1, that stands for 3. And next number, well, you don't have a symbol after 1, so you start with 0 again. So you repeat, so you add one more digit. So this is how binary number works. Okay, same thing happens with hexadecimal. Now hexadecimal, you have 16 symbols to begin with. 0 to 9. 0 to 9, then after that you use A, B, C, D, E, F. Okay, that's how it works. Okay, these are important because when you talk about encoding, you have to deal with, it comes down to, that's what computer stores, binary number. Why do you need hexadecimal once you have, because computers are just binary numbers, why do you have this hexadecimal? Well, the reason for that is that hexadecimal number is a very compact way to represent binary numbers. Because if you use binary numbers, then even a short number, let's say 8, you have to use 3 digits. You have 3 digits. But if you have, let's say, 1,000, you want to represent 1,000 by binary number, what do you get is, let's say 1,000. So here is so you have 1111101000. Pretty soon you have like a huge sequence of binary numbers, which is unmanageable and hard to process to the human brain. That is why, okay, I'm telling you, so this is the reason you have hexadecimal numbers. Otherwise, you don't need it. So hexadecimal number is a a human notation is a way to represent binary numbers in a compact way. Okay, so each hexadecimal numbers represent 4 binary digits. So if you have a hexadecimal of 1F, you can fairly easily translate to binary. There is an algorithm, but I don't know it. Anyway, so that's about binary numbers, and that's about hexadecimal numbers. Okay, eventually you need to be very familiar with them. Okay, so let's go back to encoding. So encoding is a way to transform each character to binary digits. Now let's talk about how do you do that. Okay, so first of all, you need to have a kind of a standard agreed upon way to say what T becomes. For example, you have a list of characters, and what is a binary sequence for A. You have to agree on that, because otherwise my computer says A is 65, your computer says A is 64, we don't agree, then it's gibberish, So that is why, so you need a standard, so it becomes a standard, okay? So one of the standard is called ASCII. Okay, so one of the standard is called ASCII. So let's see, ASCII characters, in the beginning, because computers are mostly created in USA. So, and the language is English. So we have ASCII characters. ASCII characters are these sequence of symbols, okay? There's no smiley, there's no emoji, there's no arrow, there's no acute E, for European language. There's just English. So standard English, lowercase, uppercase, and punctuations, parentheses, equal sign, and numbers, and some punctuations. Okay, that's the ASCII character set. Remember, so this is a standard. So, this is created by American Standard Code for Information Exchange, created in 1960s. So that way everyone can agree what each character is what number. Okay, so for example, then here's a table. Okay, let me show you. So for example, the A character in decimal is 65. In hexadecimal is 41. In binary, you can convert it to binary. It's 0, 1, something. Basically, seven digits, binary digits, 7 bits. Okay, so ASCII standard is a standard that says each character is given a character ID. Okay, a decimal. Then you can convert the decimal to hex or binary. Okay, but the essential thing is that you assign each character an ID, basically a number, okay, an integer. So you have all these numbers, okay. So that's ASCII. That's the earliest 1960s, just for English. So let me talk about encoding. So encoding is a way to transform characters to sequence of binary digits. In order to do that, you need a standard. You need an encoding standard. So ASCII is one of the first one. This is all critical, because without some kind of encoding, you can't do computation. You can't do electronic computers. So this is standard. Okay, ASCII is the very first encoding standard. Now let me talk about character set. Okay, character set is just a set of characters. For example, ABC is a character set. ABCD is a character set. Let's say A and 0, just 2 characters, that's also a character set. So character set is just a set of characters. Now, why is it important? Because it's important because when you define a standard for encoding, you implicitly defined a character set. For example, for the ASCII, your character set is these, You don't have emoji, you don't have right arrow, you don't have acute E, and so on. So character set is just a set of characters. That's the the most basic idea. So once you have a character set, you say in your standard, this is a set of characters that we try to define. Okay, so you start with a character set, then you say what each character should be what number. Okay, standard. Everyone agrees on if they are using your standard. Okay, so that is a character ID. This is the essence of encoding standard. This is the most fundamental essence. Give a numerical ID to each character for every character in your character set. Okay, that's the essence. Give an integer ID, and this integer ID today is known as Codepoint. Okay, we'll start to talk about Codepoint. Codepoint is just an integer ID for every character. So especially important in Unicode. We'll talk about Unicode in a bit. But basically, Codepoint is just a number assigned to every character in your character set. Okay. For example, in Unicode, the lowercase a is 97. Okay. Then you can translate it to hexadecimal and others. Okay. So the character alpha, the Greek alpha, has a number code point 945. Okay, that's alpha. And this emoji face with tears of joy has this ID 128514 code point. Okay, so technically it's called code point, but you can just think of it as character ID. That's much simpler. Okay, so remember again, every character has a character ID, an integer that stands for the character. And this character to ID is the most important thing. It's the essence of encoding standard. Okay, once you know this, then you can convert any text to computer sequence of binary numbers, or vice versa, binary numbers you can start to read the file. When you read a file, for example, let me show you this interesting in Emacs. Hexamod. Discard undo info. Okay. So you see, we are looking at the same file. Hold on a second. Let me show you. Okay. What? Okay, so what did we, okay. So you see, let me show you, okay. Save a copy. So here is today's talk show, right? Today's talk show HTML file. So you can see it's a HTML file here. Now I open it, it looks like this. Readable, it's just HTML with English. Now, but when this file stored in your computer, it's actually just a sequence of zeros and ones. So when you open it, you actually need to decode it. You need to turn the sequence of 0 and 1s into readable characters. So let me show you one way you can see that. So in Emacs, you can call hexamod. Okay. So this is how that file looks like in hexadecimal. So it begin with 3C21 646F. That's what the file looks like in hexadecimal, and you can turn this hexadecimal to binary numbers. Okay, so that shows. Okay, so encoding. So we talked about character set. We talked about character encoding. That's turning characters to binary numbers and vice versa. Then we talked about character encoding standard. Okay, we talked about ASCII, character encoding standard, one of the earliest for English characters only. Then beginning around year 1991, the Unicode begin. Why does it begin? Because in the early days, 1960s, there's no internet, so computers are created in America, USA. So we just am I still going comments? Okay, comments, and let me check check video, check, yeah. So USA created computers. We created the ASCII encoding, but we don't have Chinese, because Chinese, we don't have Japanese. We just for English. So, but eventually, people in Europe, French, they need acute E, and they need a bunch of other characters. Iceland, Nordic, German languages, you need some other characters. So you started to have encoding standard for European languages, like IEC 8859. So that's another encoding standard. So starting around 1980s or so, 1990s. But so around 1991, the Unicode consortium began. So why? Because you have ASCII encoding, which is great for USA, but Europeans, they have, each language, they created their own encoding. For Spanish, Spanish needs the N with tilde, that's not in French. French needs some of their own. In German, you need umlaut, So each country started to have their own encoding for their language. So it became confusing. So someone's thinking, why don't we have one universal encoding system? We define a character set. A set of characters that encompass all languages, including Japanese and Chinese. So we have one single universal encoding, universal character set. And for each character, we assign a number. So this is universal. So when a computer reads a file, you can just look up this universal encoding. You don't have to check or guess what encoding is it used, because if you got the wrong encoding, decoding, you got gibberish. So that is the idea of Unicode. Begin in 1991. Okay, so that's the idea of Unicode. Okay, so now let's see, 44 minutes. So let's quickly finish, almost done. Okay. So Unicode begin. Okay. So now let me tell you about what's the Unicode. So Unicode is an organization, Unicode consortium. The idea is that one single encoding for every language, universal. Okay. So but it has some bumps, some evolution, So in the beginning, they think that for every character, we're gonna start with 16 bits. Okay, so let me think about what I want to talk about in the rest of the video. Okay. So we covered character set, we covered encoding, and as a consequence, you need an encoding standard. And the essence of encoding standard is to define a character set, and for each character, you have a number corresponding to it, character ID or code point. Okay, but in 1991. The idea came up that, why don't we have one single universal encoding, just one encoding that includes every character in every language. Okay, so that started to become popular, and by year 2000, Unicode started to replace all the other European specialized encoding used in Europe and Japan. Okay. So Unicode became popular. Okay, so let me talk about what does Unicode defines exactly. So Unicode. So let me explain a little bit about Unicode and history. So we also talked about encoding standard and what they define. As remember, it's a character ID. That's that's the essence. So character set and encoding is different. Character set is just a character set, okay? Encoding is a way to turn a character into a number, okay? And what is a Unicode? It's it's an idea of one single encoding for every language. And Unicode character set, so what is a character set in Unicode? It includes every character in every language. That's the idea, okay? So we also explained Codepoint, which is just a number assigned to a character, okay? Now, character name is also simple to understand. Each character, for example, the capital A, there's a name, capital A, or you call it Latin capital A or English capital A. So usually, almost always, each character also has a name. So in Unicode, they just standardized the name. So in Unicode, every character has a name, and this name is always unique. For example, here's some examples. So capital A, the name in Unicode assigned to this character is Latin capital letter A, okay? And this is unique. And for the Greek alpha, it's Greek small letter alpha. And also, by the way, the Unicode naming for characters, they are always all capitalized, and they are always ASCII. Okay, so you want to see a cute E or something. So every character has a name, okay? But however, because of the, this is a huge project. Unicode encompasses all human languages, past and present. So in this process, in order to design, in order to assign a number to every character, you have lots of problems. This is no small task, because you have dead languages that requires research. Egyptian, for example, some of the dead languages, hieroglyph, linear B, Phoenician, Run, and you have also constructed languages. Deseret. Let me show you some of them. Cuneiform. 300. This is 5,000 years ago. 5,000 years ago. So if you are Unicode, if you are one of the Unicode designers, first of all, how do you know? Well, how do you know what characters are there? You don't know. This is 5,000 years ago. 5,000 years ago. Cuneiform. So how do you know? Well, you consult, historical linguists. It takes decades, hundreds of years to come up with what characters are there. And then you might be missing some characters. So the Unicode task is not easy. It's still an ongoing process. So we are looking at some of the dead languages. Today you also have Egyptian hieroglyphs. This is again 3,000 years ago or 4. Egyptian characters. By the way, there's an interesting. Now here is the clickbait. Okay, you see this cock, these penises. These penises are censored by Microsoft. In Microsoft Font, they display as squares. Okay, censored. And here is an artifact, a photo of the Rosetta Stone, very famous for. It is because of this stone, someone dug up. You can look up Wikipedia. Someone dug up in. So this stone is around 196 BC, so 2,000 years ago. And because of this stone contains 3 languages. Then people started to finally, for the first time, to decipher the Egyptian, hieroglyph, to begin to understand what it means. What all these birds and cocks, and they also have, this is Asian. This is not like today's social justice thinking, whatever. You have cocks, of course. You have penis, then you have the birth, childbirth. You see, that's part of humanity. That's Asian. Then, so you have all these, quite interesting to look into. Okay, so there's a lot. Then there's a linear B. On Microsoft Windows, they don't show but on the Mac, by default, you can see these are linear B characters. This is also 4,000 years ago. 4,000 years ago, linear B characters. Okay. Then you have the Phoenician. This is for English, this is the granddaddy of English alphabet. English alphabet came from Latin. Latin came from Roman, and then Roman came from Latin alphabet. Latin alphabet came from Greek, derived from Greek alphabet, and Greek alphabet is derived from Phoenician. Okay, so these characters you see here in Unicode, those are Phoenician. Those are the granddaddy of the English ABCD. Okay, so the point here is that the Unicode is just a tremendous project encompassing lots of things. Okay, so the reason we are talking about this because if you want to define a standard, an encoding standard, if you want to define a encoding standard, first of all, you need to have you need to precisely specify a character set. But one of the big problems is that when it comes to Asian languages, what character set are there? You don't even know. You don't know. So it's a huge project. That's just one of the problems. There's other problems, like when you have Chinese characters is also Asian. Let me show you. Okay, so Chinese characters. Okay, so here, so you have some of these characters 4,000 years ago. This is called oracle bone. These are precursors of Chinese characters. Then you can see this heavy cauldron from 782 BC. So it's about 3,000 years ago. And you can see huge number of Chinese characters in it. And those are actually legible, almost the same to today's, so you have these things, Chinese characters, okay. Very close, okay, actually not the same as Chinese, but by this time 3,000 years ago, you have these characters, and these are almost the same as Chinese characters used today. So anyway, so the issue with Unicode is that what are the character set, and you need to give a number for each one of these characters. Then it gets more complex because Chinese characters is then used in Japanese. Eventually became part of the Japanese writing system and used in Korea and also used in Vietnam. But over the 1,000 years, they diverged somewhat. So Japanese has their own way to write the same character, slightly different. You might think of them as different font, but cultural differences. So do you give the same characters, the Japanese version, a different? Do you consider them as a different characters, or do you consider them as just the same character but using a different font? That's an issue and very controversial as well. So that's one of the big controversy in Unicode called hand unification. Lots of issues. So what I'm talking about is the creation of the Unicode. It's no simple task, okay? But let's go back to encoding and stuff, okay? So encoding, so character set ASCII. So what does Unicode define actually? So Unicode, what Unicode actually defines? So Unicode, you begin with a character set. Unicode by now, every year there's a new version of Unicode. So by today is Unicode 11, Unicode, every year you have a new version. So they kept adding new characters. Meanwhile, they try to maintain backward compatible so that you can't just change randomly. But each year they kind of add more characters. But what does Unicode actually define? So this is becoming complex. Let me explain this. So before we talked about encoding, right? An encoding standard is a standard that defines a character set. Then for each character, you give them a unique ID for the character. Okay, that's an encoding standard. Now, Unicode begin like that. So when Unicode began in 1991, they think that, okay, the total number of characters we need is at most 16 bits. 16 bits, that means 16 binary digits. Okay, so let me show you. So let's go to byte order. Well, let's not go over. Let's just let me just talk about. So I'm talking about what does Unicode actually define. Okay, essentially it defines. Let me tell you. Okay, it defines two primary things defined by Unicode. One is a character set, and the character ID for each character in the character set. Okay, that's what Unicode defines. So you give each character, you give them an ID called the Codepoint for that character. That's the most important thing Unicode defines, and so let me show you. Codepoint. Okay, so like that we showed there. So you have a character, then you have a Codepoint, and also you have a name to go with it. That's the most important thing Unicode defined. Now the second, also equally important, is actually encodings. Okay, so Unicode actually defined several encodings. Okay, let me explain. So Unicode, in the beginning, they defined. So we have to go to Unicode history. So Unicode defined several encodings by now. Okay, so you have UTF-8. And you have also UTF-16. But in the beginning, Unicode thinks the Unicode people, they want to have a universal encoding system for all the world's languages. So they thought that 16 bits is enough, meaning 16 binary numbers. Okay, so here's a link I want. So let's go to binary numbers. So let's see what 16 binary digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. 16 binary digits. Okay, so actually I need to type the binary digit here. So in decimal, that's 32,767. The Unicode people think that 32,000 characters is enough for all the world's characters. Okay, in the beginning they think this is enough for all the live languages. They are not counting dead languages. But eventually, over the years, people decided that actually we need all the Egyptians. We need them to be part of the Unicode. So they So eventually, in the 1990s, they realized 32,000 characters is not enough. Okay, that's a problem. In the beginning, they think 32,000 characters is enough. Therefore, you just need 16 binary digits, okay, or at most 4 hexadecimal characters to represent any character in any human language, okay. But over the years, they changed their mind. They begin to think, oh, actually, that's not enough. So they started to extend it. So you started to need more than 16 characters, 16 bits. So in the beginning, Unicode is, they defined their encoding called UCS, okay, 16 characters. But eventually they realized that's not enough. So they created a encoding standard called UTF-16. And so in this UTF-16 encoding, it's a variable width encoding. Okay, so I need to explain that. This video is actually kind of too long. I think am I doing good? I'm just starting to get very boring and too slow. So let me, so we are talking about what are the different encodings of Unicode. Okay, let's talk about that. So in the beginning, Unicode thinks that 16 bits is enough, which is 32,000 characters. Eventually, they realized that's not enough. But in the beginning, Unicode defined encoding. Today is called today you call it UCS, Universal Character System or something like that, UCS encoding. So every character corresponds to a number that is represented by 16 binary digits. Okay, that's the original, the first Unicode universal encoding. Okay, every character corresponds to a number that's 16 bits. Okay, but they realized that's not enough, so they started to define UTF-16 encoding. Now, UTF-16 encoding is such that, remember, every character has a character ID, which is an integer. You can translate the integer, represent the integer in a decimal, in a binary notation. But in UTF-16 encoding, because some of the number is bigger than 32,000, therefore it needs more than 16 binary digits. So UTF-16 encoding is such that for some characters you need 16 binary digits, but for some other characters you need more than 16. In fact, you need 32 binary bits, binary digits. So for some characters it's 16 binary digits. Other characters is 32 binary digits. So that is the UTF-16 encoding. Okay, so this happened in the early 1990s. So in the beginning, Unicode is called UCS2 encoding. Every character is just 16 bits. But in 1996, they decided that's not enough. So they created the UTF-16 encoding. So in UTF-16, every character may be 16 bits or 32, depending on the character. So that's 1996, and it is embraced by JavaScript, okay, by also the Java language, and it's also embraced by Microsoft's NTFS file system. That is in your in your files and directory, the character names, you have name for the folder or files. Those are encoded on Windows. using the NTFS file system, and those are encoded in UTF-16, okay? And it's also used by Apple's HFS Plus file system. Now, Apple's file system, HFS Plus, is used between 1998 to 2017, okay? So UTF-16 is used by this system, so fairly popular. Okay, that's one of the encoding Unicode defines. Okay, remember we are talking about what does Unicode defines. Unicode defines a character set, defines the character ID or code point for each character. Then it defines by now two encodings. One is the beginning UCS 2, so-called today. That's the original encoding. Each character is 16 bits. Then in 1996, they invented UTF-16 because they think that 16 bits, 32,000 characters is not enough. So they created UTF-16 encoding. So each character is now 16 bits or 32 bits, depends on the character. Okay, and this UTF-16 encoding became fairly popular in the 1990s, used by several programming languages and many other technologies. Okay, that's UTF-16 encoding. Now, how it actually translates into a character, we will talk about. I'm not gonna cover because this video is too slow than I thought. Okay, so that's a history of Unicode. Begin with USC, the original version, USC2, then UTF-16. Now let's talk about UTF-8. Now UTF-8 is now today's universal. It's actually the most common UTF-8. Okay, so UTF-8, UTF-16 is a problem. It's a problem for the Unix people, and because UTF-16 is not compatible with ASCII, because in UTF-16 every character is 16 bits or 32 bits. Okay, so-called variable width encoding. Because each character is either 16 or 32, depends on the character. But it's not compatible with ASCII, because in ASCII encoding each character is just 8 bits. In fact, 7 bits. But usually a computer unit, the minimal unit is 8, because that's a power of 2, 2 raised to the third power. So 8 bits is a minimal unit. In ASCII encoding, every character is 8 bits, but it's not compatible with UTF-16. So what does that mean? That means every Unix, the whole entire operating system, all the tools, grep, bash, they need to basically all be rewritten from scratch to deal with characters, text processing. This happens in Python 2 to Python 3. That's why this is a major reason Python, the Guido von Rossum created Python 3. Because in Python 2, this is a huge problem, huge headache, because all the software before UTF-16 or before Unicode is just not compatible. You have to rewrite the whole thing, every tool. So the ROP pike, there arise the Unicode, the Unix phonetic ROP pike. Let me show you this interesting history. Okay, ROP pike invented the UTF-8 encoding on a napkin. Okay, and here's his article about the history of UTF-8. Essentially, he and Thompson, another Unix guy, what's his name? Ken Thompson. Yeah, I believe that's Ken Thompson. But anyway, that's a history of UTF-8 creation. So you have UTF-16 which is incompatible with ASCII, creates a huge amount of headache. But the Unicode people, they know the problem, so they created another encoding. They tried, but when they sent it to Rob Pike, when Rob Pike and Ken Thompson see it, that's no good. They are very bright. They can see that, they can tell right away. This new proposal got several problems. But so eventually basically they created UTF-8. They invented UTF-8 on a napkin in a restaurant overnight, and implemented, write the whole spec in 1 week, about 1 week. So this happened in 1992. Okay. So they created UTF-8, which became today is the most popular and the best. Okay, because I spent a lot of time studying UTF-8. In the past month or so, it is actually the best encoding of them all. And UTF-16 is no good. Okay, you should make everything UTF-8. Okay, so why is it so great? So first of all, UTF-8 is ASCII compatible. That means if you have old file, before 1990s, before Unicode, old file, ASCII file, it's totally compatible with UTF-8, meaning that if the same file encoded in UTF-8, it's identical to ASCII. Okay, so you no need to change. All the Unix kernel programming languages, Bash, grep, all the tools, no need to change. Okay, it works still. So that's one of the most powerful reason UTF is the most popular today, which is great. Thanks to Rob Pike and Ken Thompson. UTF-8, fantastic. Now UTF-8 is a variable width encoding, meaning that each character is represented by 1, 2, 4 bytes. Okay, 1 byte is 8 bits. So it's either 8, each character is either 8 bits or 16, or maybe 24 or 32. Okay, 1, 2, 4 bytes. So depending on the character. So that's the nature of UTF-8 encoding. So you might think, oh well, that's no good, because then you don't know how, you have to look up how many bits is a byte, because usually variable length encoding is a problem. Yeah, that's true, but the alternative is that you encode every character as 32 bits, but that's a huge waste of space. Because if you do that, then every file will become 4 times larger. 1 megabyte file becomes 4 megabyte. Then you have the fixed width encoding, meaning that every character is always 32 bits, which makes programming easy. But however, it's bloat every time. Everything is increased by 4 times, especially when you have to save, load the file in memory. So if you have 8 gigabyte memory RAM, now it becomes not enough. So lots of problems. So UTF-8 is actually the best. Okay, it's the best, and it's the most used on the web. By now it's used by 97% of all websites. UTF-8. So UTF-8 is great. So UTF-8. So let me go back to summarize. Okay. So, by the way, you can see here's a UTF-8 encoding scheme, and it's very simple. There's lots of great properties. Okay, if you get down to how exactly a character becomes, the binary sequence. Now, let me kind of summarize what we talked about before. Now, remember encoding. So, what is encoding? Encoding is a way to transform a character into a sequence of binary numbers. Okay. Now, what do you need in order to do that? One is that you need to define a character set. Now, in the case of Unicode, the character set is all the world's languages characters. Okay. So more than 32,000 of them. So you have a character set.
Then you need a character ID, the code point, meaning that for each character, you give it a integer ID. Okay, that's the code point. Okay, we have that. Then the next thing you need to do is the actual scheme of encoding. So given a character, you know the character ID, which is a number. Now the problem is that you need to turn this number into a binary digits. Okay. Now that's easy, right? Because every number you have a binary digit notation representation, but it's not just that, because computers comes with a unit of bytes. One byte is 8 bits. You cannot have 10 bits. You can, but then you need padding. So encoding is turning a number into binary sequences. And so far, we talked about 4 ways to do that. One is ASCII. Okay, every character is just 8 bits. ASCII. In fact, for the ASCII character set, you only need 7 bits. So what you do is you just add an extra 0 in front. So you have 8 bits, 1 byte, ASCII. Every character is 8 bits. Now you have original Unicode encoding. Today we call USC2. In that encoding, it's obsolete. But in that encoding, each character is 16 bits, okay, fixed. Now that's obsolete. Now you have UTF-16 encoding. You have UTF-16 encoding, where every character is either 16 bits or 32 bits. Then you have the UTF-8 encoding, where every character is 8 bits to 32 bits, 1 to 4 bytes, okay? And this is compatible with ASCII, so this is the best, okay? I think that's it for today. This is now close to 90 minutes, and it's probably boring, but I was thinking to cover them in a condensed way, 30 minutes, but okay, but let me go on. So just to finish, so we covered Unicode. Now let me recap. Unicode is an encoding, it's a Unicode consortium beginning in 1991. The idea is to have one single universal encoding for all the world's languages, characters. So it began by thinking that 32,000 characters is enough. So they created, they defined a character set. They defined a unique ID for each character. Then they defined a encoding. Today it's called CS2, which is obsolete, okay, where every character is 16 bits. But then Unicode realized you need more than 32,000 characters. You need more than 32 bits. So they created UTF-16 encoding, which became very popular. But then the Unix people, the Unix fanatics, Rob Pike and Ken Thompson, they saw the problem. They think, UTF-8, UTF-16 is no good. We need a ASCII compatible one. They created UTF-8, which is variable width, and it's fantastic, okay? And now it's universal. It's used by 98% of websites, including all Chinese. We haven't talked about Chinese encoding here, but there were Chinese encoding, because in the 1980s in Taiwan, they started to have computers. They need their own encoding. So Chinese encoding, an introduction. You have, in the beginning, 1984, you have Big 5 encoding for Chinese characters used in Taiwan and Hong Kong. Then China in 1980s decided, they need one too. So they created GB 2312. Now this is actually ASCII compatible. I don't know if Big 5 is ASCII compatible, but anyway, the China's GB something extended into GBK encoding, kind of backward compatible extension. Then GBK extended to become GB18030. Again, backward compatible and compatible with ASCII. So it's required by law in China. Everything you do should be support this encoding. And this China encoding is actually Unicode. They are compatible with Unicode. It's considered Unicode transformation format. Okay, that's what UTF stand for. You have UTF-8, UTF-16. What does UTF stand for? That stands for Unicode transformation format. And what does Unicode stand for? Unicode stands for Universal Characters Code. So this Chinese character set is also universal transformation format. Okay, it's compatible with Unicode. So even in China today, if you look at all the Chinese websites, for example, I did a survey last month, a few weeks ago, looking at all the most popular Chinese website. What do they use? UTF-8. Okay, they actually also use UTF-8. Quite interesting. Okay, so that's about it for today. Now let me talk about surrogate pair. Okay, surrogate pair is something that came out of UTF-16, which is a abomination. Now remember, originally Unicode thinks that 16 bits is enough, but it turns out not enough. So they created UTF-16, where a character may be 16 bits or 32, depending on the character. So when you have a character 32 bits, what do you do? Basically, they pick some number, in the 16-bit space that's unused character. Okay, unassigned number, unassigned code point. So they pick something in that range, then two of those units together, each unit is 16 bits, two of those in an unused range. If you have two of those, they say that stands for a character that's more than 32 bits. So that's what surrogate pair is. Surrogate pair. This is nasty. Okay, surrogate pair creates lots of problems. So that's one of the problems. That's why UTF-16 is no good. UTF-16 is no good because it's not ASCII compatible. Then you have the surrogate pair kind of a hack. Because remember, UTF-16 happened because originally, they think 16 bits is enough, but then it's not. So they try to extend it, but in a backward compatible way. So that's why you have UTF-16 and you have surrogate pair. Okay, so that's some technical point. Okay, I think that's it for today. In email system, everyone uses the same encoding. Yeah, well, today it's all UTF-8, especially if you use Google, because in email, it's today basically you just have a few handful powerful centralized corporations that runs email, because they try to prevent, ideally with the email protocol on internet, everyone can create an email server, but not today, because all the giant, they prevent you to do so in all sorts of ways. So and also because people became lazy, so it's not like the 90s. In the 90s, everyone, if you are a nerd, you can, if you run Unix or Linux, you can start your own email server. And but not today. It's very hard. So you just have Microsoft, Yahoo Mail, Microsoft Mail, Google, and a handful. They control all the email. Why? Because they can look at your email content with the collaboration of USA government and other big governments such as China. They prevent you from creating your own email. But so in email mostly it's I don't know the details, but you can look up the email protocols have changed over the past 20 years. But I'm pretty sure if you use Google Mail, for example, it's all UTF-8. Okay, there's a question about the expos comparable to Kinesis. I'm not going to explain that. Watch my other videos. Okay, that's it. Bye, guys. If you like my stuff, donate, okay? PayPal, Patreon me. Go to my website, xali.info, and all the way down, you can see Patreon, or buy me an Amazon gift card, or PayPal me, or you can also Bitcoin me. And you can get my entire website content if you give a big gift of $300. I'll send you, this is like 1 gigabyte, all sort of content and information, okay? You can also buy my Emacs tutorial, my Emacs tutorial, my JavaScript tutorial, independent, I have like 800 pages of JavaScript in depth. Okay, if you like my stuff, support me. There's a question about deleting emails. Do deleted emails actually leave a server? That is the best way to do this. Basically, there's no way to delete emails, okay? That's a new concept. The deleting email is a new concept, maybe from Google Gmail or something, they added a feature. But as far as I know, the email protocol, there's no way to do it. Once the email is sent, it's sent. You cannot delete it, okay? So I don't know. I don't actually know exactly what Google Gmail do when they offer you a delete email, but basically that's impossible. So don't think about it. Google might have I don't think it's possible. Once email is gone, it's out. Okay. Bye, guys.